Hello. You should see the desktop and you should hear me. Is everything okay?
Yeah, seems okay.
Okay, great. Let me pull up some windows. Okay. Okay. What we're going to do today, well, I put a bunch of examples of recursive functions up here. One of the things we'll do today is go through them. There's like 20 examples of recursive functions here. And what we're going to do is just use them as a way to get a feel for how to use recursion. Okay, so I try to create a variety of examples that go from pretty simple, straightforward recursion. At the end, there's a couple kind of little bit tricky ones. Okay, so that's one thing we'll do today is just do lots of examples of recursion, because the next chapter of the textbook, right now, we're kind of talking about polymorphism. We've been talking about polymorphism a little bit off and on, but that's chapter 9 in the no, that's chapter 8 in the book. The next chapter in the book after 8 is something called higher order functions. Higher order functions, which gets much trickier and currying. So what we want to do is think about recursion in its basics. The textbook doesn't really talk about recursion that much. It kind of assumes that you've seen recursion in a previous course, usually either data structures class or algorithms class. So the author of this book kind of assumed you've seen basic recursion before. So he doesn't do many examples. That's why we're going to try today to do more examples. The higher order functions make a really lot of use of recursion, and really, and in kind of a tricky way. So to be ready for chapter 9, it's real good for us to spend some time just doing quite a few more examples of basic recursion. Okay. And as we do it, we'll talk more and more. We'll talk more about polymorphism. Polymorphism is something that's going to just keep coming up as the semester goes along. So we'll talk about polymorphism as we're going along. We'll see examples of it. But what we really want to do today is do a bunch of examples of recursion. Now, at the same time, I gave you a bunch of problems to work with, because I think the best way to learn this stuff is just use it, at least even in small ways. So there's 3 kinds of problems out there right now. There's these type declaration problems, pattern problems, and the third one let me find it. There's 3 kinds of problems out there. Okay, let me close these. There's these problems where let me close these. Okay, starting at the top, there's these kinds of problems here where you have to you write these things using patterns. They're written without patterns, and you have to write them in the better way using patterns. So that's practice with using patterns. Okay, so there's these problems where you have to write the functions given to you in kind of the old-fashioned Java-ish way without using patterns, and you have to translate it into a pattern problem. You have to turn it into something that uses patterns. Okay, then the next kind of problem is I give you a type and want you to come up with an example, any example of a function that has that type. So you have to come up with a concrete example, make it as simple as possible. In fact, the goal of this assignment is what is the simplest function that would have that type, okay? And quite often there's only really one, or there isn't much choice, okay? But that's an interesting kind of problem. I give you the type, you have to find a formula, a definition for that function, okay? So that's another kind of problem. And then the third kind of problem up there, translate from functions to patterns, translate types into functions. And then there's these problems. The third kind were to annotate the types, to look at this function definition and figure out what is X, what is Y, and what's the return value of this function. Annotate the function like you do in Java. And so you notice that ML looks like JavaScript because you don't say what X is and you don't say what Y is, but ML is not like JavaScript or Python. X has a specific type, Y has a specific type. You can leave it up to ML to figure it out, but you're actually better off trying to do it yourself. And many ML programmers will annotate their code with what type is X, just like Java would make you do, or C++ would make you do. What's the type of Y, and what's the return type of the function? So these problems ask you to, now the reason every function is defined 2 times, so that you can annotate the second version, and then ask ML, does the first one and the second one have the same type? Because you don't want to goof up the type of the second one. So it's set up so that you can annotate the second one and then ask ML for the type of each one. So if I download that, we'll just do a couple more. We did a couple of them the other day. Okay. That's the, well, actually, let's download this. Okay. Now this is where polymorphism, some of these types are polymorphic and some of them aren't. The polymorphic ones are the ones that have a type letter in them. Okay. And the other ones are called monomorphic. They don't have any type letter in them. Okay. So okay. Here, like we did this example, X takes in an int, and X returns, and remember, this was to show you that the syntax is a little bit quirky. That says that the input is an int. That actually says that the output is an int. This notation is the same as this notation. The grouping here is X is the input and this is the output. So this just kind of makes the grouping more obvious. And then here I put the type on the input. So X in, int in, int out. Okay. So this is the right way to write it. This one only declares the output. This one only declares the output. This one only declares the input. Okay. And this one is what we want. Declare what the input is and what the output is. Okay. Okay. And here's another one. Again, here, since you're taking the real of X, okay, that tells you that X has to be an int. Here, what tells you that X is an int is because you're adding 1 to it. So you're adding 1 to it. So since you add 1 to X, you can't add 1 to a real number, so X has to be an int. Here I'm adding 1.0 to something. What I add it to is a real, but then I'm taking an input here. Input to real is got to be int. So that means X is int. So even though I take the int, convert it to a real, then add it to a real. Okay. So the input is int, but the output is real. Okay. And then here, this one only declares the output. See, the syntax here is the colon equal is actually the output value. Again, this is actually still declaring just the output. So you got to be careful about reading it. It looks like it's declaring the input, but it's really declaring the output. This one, again, is still declaring. So all of these are the same. They're only declaring the output, but the notation's kind of tricky. This is how you declare the input. You have to group it to say that you're declaring the input as an int. Okay. All right. Let's see. Let's try one that we haven't done. Okay. So we did these. So like this one here. Okay. Okay. You've got something, and you're converting it to a string. But that toString method comes out of the integer package. So that means that this guy is an integer being converted to a string. Okay. Now, so that means this guy is, and also that agrees with this. This guy is the input to the real function. The real function converts int to real. So that says that X is an int. Well, now what I just typed is wrong. That says that the function returns an int. So to make it that X is an int, I have to group it. Okay, so X returns it. So X is an int in. Now what comes out is a pair. So what comes out of the function is a pair. Now the pair is got a real in the first part, and it's times. The way you write pairs is you write the type times the other type. The other type, well, we said we're converting this int to a string, so the other type is string. Okay. And then if I want to check this, I could just open up ML and copy and paste these two guys in. Okay. Notice that it auto-loaded this integer library. Yeah. So there's a little bit messy there. If I do it again, the auto-loading is done. So now I don't see the auto-loading. And I see that the type of Q1, that's the one I didn't annotate. It's int goes to real times string. And then the one I annotated, it goes from int to real time string. So I annotated it correctly. Okay. So Q1 is not annotated, Q2 is annotated, but I annotated it correctly. And if you goofed up the annotation, like if you take this one, and if you, oh, my key, I still have this broken key. I have this broken control key on my keyboard. Makes copy and pasting really hard. If you goof it up, for example, you say, oh, it looks like this thing takes in a real. ML tells you that you typed it wrong. It knows what the type is. From the right-hand side, it knows what the type is, and you annotated it wrong on the left-hand side. Okay, so it's going to tell you here what you did wrong. It's not so easy to read. Sometimes it's easier just to go back and stare at your code. But if you read the error message correctly, you'll see operator and operand do not agree. Okay, operator. Now the expression is real x. That's the operator. So the operator has domain int. Real takes in an int, but I gave it a real. Okay, so that's because I said x is a real. So what it's saying is I said here, now it's taking me for my word, x is a real. So then it goes over here and says, but you can't put a real into the real function. Okay, so it read it from left to right. So it said that you said that x is a real. So that means this is the mistake over here. From our point of view, the mistake is really over here. We wanted it to be this function, so this should be an int over here. But ML reads it from left to right. So ML says, you said that x is a real. So then it goes over and keeps reading and says, but that doesn't make sense over here. You can't take a real number as input to the real function. The real function takes in an int. So the operator's domain is int. The input to real is int. The operand, which is the x, the operand is real because we set it over here. And the expression they're worried about is real of x. Okay, so what the operator should take, what the operator is given, and what operator they're talking about. Okay, now they actually found another mistake. Okay, the operator's domain is int. The operand you gave it is real, and it's the expression int to string x. Well, it didn't like this one either. This one has also got a mistake. If we say that x is real, then you can't put a real into the integer to string function. Okay, so it found two mistakes. Okay, now I can go back and fix that. Now, for example, if I fix it and make this right, but make something wrong over here. Suppose I think this is int. So I think it puts out it takes in an int and gives me back an int string. Okay. Again, I got a mistake. Okay. Read error. Right-hand side of clause does not agree with function. Okay. Now notice that here now it's saying that the right-hand side doesn't agree with the declaration on the left-hand side. So right-hand side of clause, each equal is a clause. So these functions only have one clause. When we get to our recursive functions, we're going to write functions with multiple clauses. Each one of these is a simple function. It only has one clause, only one pattern. Okay. So, but they call each one of these lines with an equal something is a clause. Okay. Okay. So the right-hand side of clause does not agree with the function result. Oh, they're telling us we've got the return type wrong. Okay, the result type, the return type. So the right-hand side has got the wrong return type. Okay, what we're computing is real-time string. We're computing real-time string. No, let's see. No, what we want is real-time string. We should be getting real-time string. That's what we declared. No, let's see. Which one are we reading as that? Oh yeah, this guy is computing real-time string because it's computing a real here and a string here. So it's the expression is real-time string. The result type is supposed to be int times string. See, we declared it to be int times string. We're computing real-time string. Okay, so this is what we're computing on the right-hand side. This is what we declared should be on the right-hand side. And then there's the clause that's a problem. There's the whole thing. There's that clause. Okay, so they're saying the right-hand side is returning a different type than what the left-hand the left-hand, oh no, here it is. The function type x takes in an int in this clause, and it's supposed to return that type there. It's supposed to, well, there's the formula along with its type. Actually, it's kind of a complicated thing. What it's saying is that the function x takes in an int, and it returns this formula, which has this type. Okay. But it's actually computing real-time string, not int-time string. It's supposed to have that type. Okay, so these error messages are not easy to read, but so's Java's error messages, and so are C++'s error. C++'s error messages are probably even worse. Okay, there's very few languages that have good compiler error messages. It's kind of rare to find a compiler that has real readable error messages. So ML's no worse than most of them. Okay, so that's one kind of problem. Okay, I give you a function. ML knows how to type it, but we want you to type it. You figure out what the type should be. And of course, the solution to this is not to just punch that into ML and find out what the answer is, then copy it here. Okay, don't let ML do these problems for you. That's kind of cheating. It's not helping you learn the language. So don't take that, punch it into ML and find out what the answer is. And then, I mean, you still, even if you get that answer, notice that you have to take that answer and annotate the left-hand side with it. So it doesn't really give you the exact answer. It tells you what the type of the function is, but then you would still have to say, okay, that :int is the input. So that goes here in my syntax. This is the return type. So that goes here in my syntax. So in my syntax for the function, these pieces go in different places. So even if you cheat a little bit, it's not going to give you the right answer. It'll tell you the types, but you still have to figure out how to write them on the left-hand side, because it puts the types in this signature that's on the right-hand side. It gives you back this type signature, but that's ML's got a different syntax for type signatures than it has for function declarations. This is kind of a bit messy. Uh, in the language Haskell, which is kind of a modern version of ML, like Java's kind of like a modern C++, Haskell's kind of a modern ML. They fixed a lot of these problems. So the syntax for how you type the definition of a function looks like the syntax for how they tell you the type of the function. In ML, they're not the same. Here's ML telling you what the type of the function is, and it's written differently than you telling ML what the type of the function is. Okay, here you tell ML what it is. Here ML tells you what it is. It uses a different syntax, and unfortunately, it's a little bit messy. It's not too hard to go from one to the other, but it's a little bit messy. On the left of the arrow is the input type. On the right of the arrow is the output type. Okay, so there's an arrow, input type to output type. That's pretty readable. But then over here, you do input type. You put types on each of the input parameters, and then you write a colon on the last input parameter. It's the last input parameter that gets the colon to type it. See, like over here, we had two input parameters, X and Y. It was the Y input parameter that you put the colon after to put the output type. That's kind of weird. syntax, that the output type, the return type, is attached to the last parameter. Okay? And we'll kind of see why later on that that's the case. There's kind of a reason for that little bit weird. Now you can put spaces there, so you can think of it like that. You can think of it as here's the input type, here is the output type. You can think of this guy as saying on the left is the input, on the right is the output. You can kind of read it that way. Then that colon's acting like that arrow. Okay. But these colons don't act like arrows here. These colons don't act like arrows. Okay. So you could read this as separating input type from output type. Same here. You can think of this as separating input type from output type. But you got to group the input type. Here, see, they didn't group the input type. They don't need to over here because of that syntax. You've got to group the input type, and then here's the output type, return type. They call it result type. In the world of C++, Java, and C, we call them return types. And a lot of people call it the output type, what the function is outputting. But that's actually a bad thing, because outputting tends to sound more like system.out.println. So output sounds more like output that you print on a screen. So it's not a good idea to think of them as outputs. It's probably better to think of them as returns or results. The function gives you a result. The function returns something. ML always uses the phrase result type. I don't think I ever see them call it return type. It's always result type. But in Java, C++, and C, we tend to think of it as return type. Okay. So that's one kind of problem. Okay. Now let's do those. Then let's go back and do another of the other kind of problem. Okay. That was these. That was, let's see. No, what were we were doing. Yeah, we were doing, which one were we doing? We were doing these. These are the ones where you annotate. Okay, so we just did do more of these. So now another kind of was this one here, where I give you a signature and you got to come up with something that does that signature. Okay, so that was these problems. So we did a couple the other day. Let's do a couple more. Okay, like this one. Now these are polymorphic signatures. The function takes in a tuple of any two things and gives me back a tuple of the same two things, same kind of things, but in reverse order. Okay, so a type A thing and a type B thing, and output is a type B thing and a type A thing. Now, the simplest way to do that was to take in an X and a Y and give back a Y and an X. And there's probably no other way I can do it, because X has type A. I need a thing of type A over here. I have no idea what type A is. So how am I supposed to cook up a thing of type A over here? Well, the easiest thing is to use my thing of type A that I was given over here. I was given a thing of type A. I need a thing of type A. Use the one I was given. Since I don't know the type, since this is polymorphic, I'm almost forced. I think I am actually forced. I think the only function that has this signature would be this. Okay, because you don't know anything about the type of X, but you have to reproduce that type over here. So just reproduce X. You don't know anything about the type of Y, but you need to reproduce that type here. Since you have no clue what that type is, you pretty much only have to use I itself. Okay, so that type, I think you can probably prove as a theorem that that type forces you to actually write that function. Okay, here's another one. Okay, well, let's try this one here. This one's going to be a little looser. I need a pair of something and an int. Now, here this was a something and a something else. Now I'm given a something and an int, and I'm supposed to return an int and a something. Okay, well, an X and a Y. But I know the Y is an int. And I'm supposed to give back a int Well, I can do y, but I can do y plus 1. I can do anything I want with that int. Notice that with ints, since I know something about them, I could return y plus 1000, comma, but I don't know anything about x. I'm kind of stuck returning x. Okay. Notice that since I know something about that type, I can actually do a little bit with this guy here. I don't have to return the y. So this one, I can just now check it. Take that and put it into ML, and we'll see if it has the right signature. Yes, it is the right signature. Whoops. See, anything and an int returns an int and an anything. Now look what else I could do. I could even say, I have my favorite int. My favorite int is 0. And I ignore the x. I'm sorry, I ignore the y. Because I know what type this is, so I could put in a constant value from that type. Okay? See? So that's actually like the simplest thing I could do. I could just say, well, you want back an int? I'll give you an int. I'll give you back 0. Okay? And I don't even need to pay any attention to the y, because I know something about the type. When the type is concrete like that, and you know what type it is, it's monomorphic, you can say you have a lot more choice about what to do. Notice that the more you know about the type, the more things you can do. The less you know about the type, the less you can do. Okay, so a function like this I knew nothing about the types, I'm kind of forced to do that. Here, I got a lot more choice. I could do a bunch of different versions of this one. Yeah, I could return 1 there. I could return y plus 1 there. You know, I could return all these would be reasonable. Y plus, what we'll say, y minus 1. Okay, I can do I can add or subtract. Okay, all right. So I know something about the type, so I can do a little bit more. Here, I can't do much of anything. Okay, now we did this one. This took an arbitrary list and gave us a pair, where the pair was an item that is what the list is made of. Now, the list is made of these things called A's. We don't know what A is, but it's a list of these things of type A. My pair has to be a thing of type A and a list of type A. Okay, how much choice do I have here? Okay, I need to cook up a thing of type A. Okay, how can I cook up a thing of type A? Well, I can pull it out of this list. So that's one of the choices. Now that's about my only choice. My function here pretty much has to do the following thing. It's got to pull something out of the list and give me more or less the rest of the list. Okay, so a possible choice would be pull the head of the list out and give me back the tail of the list. Okay, another possibility is, oh, pull 2 things out of the list, give me the second thing, put the first thing back in. Okay, pull 3 things out of the list, put 2 of them back in, and give me the third thing. Okay, I mean, here's some other ones I could do. Here's a funny one. Oh, I'm still inside the let's see. Oh, I forgot to close that comment. I didn't realize that there was a error there. I didn't close that comment. Okay, here's another example. Here's kind of a funny thing I can do. Let's suppose, okay, the list has got something in it. I'll give you back the first thing in the list and the empty list. The empty list is a list of these things. That's actually kind of a quirky thing. The empty list is a list of those things. It's the empty list of those things. So notice I could use a constant here. It's kind of like what over here. See, I used a constant there and a constant there. Over here, I can I need to return a list of A's. The empty list is a list of A's because you gave me in a list of A's. So I'm returning to you the type that's the empty list of A's. Now, I think ML will accept this. I know it'll accept it, but I'm not sure if it's going to complain a little bit because sometimes it'll complain about it doesn't know what kind of empty list this thing is. But I think in this case it does. Let's see. Oh, what did I do wrong here? Oh, I dropped one of the colons. I lost one of the colons. Notice that single colon means type. So that said X has type X's. And then ML said, there's no type X's. So I didn't get the error message I really thought I should get. Yeah, I really, because a single colon means type of. So this is saying X is type of X's. What I really meant to say is X is const on to X's. Okay, notice how, just like every programming language, the type of operator is part of the cons operator. They have nothing to do with each other, but a little slip like that gives you kind of a weird, and actually you could even get, that could even become, if I had a type that had that happened to have a name that coincided with one of my variables, I could end up with a real subtle bug there. If I happen to have a type where the name of the type coincided with one of my variables, like list, I have a type list, and I have one of my variables. Oh, my variable is list. I can end up with really subtle error messages, real subtle errors this way, because then this could either be the variable or it could be the type, and this symbol can mean type of or cons. Okay, so that can those kind of issues can really creep up on people in the real world and lead to really hard to find bugs. Okay, now my warning is that I don't have enough cases here. I didn't say what to do with the empty list. I'd be hard pressed to define this function on the empty list, because if you give me the empty list, how do I cook up something here? So I'm going to pretty much be forced to leave this function undefined on the empty list. So I didn't define it for the empty list, but it did accept my definition. So this guy here is my return value is the empty list of type. Oh no, ML typed it wrong. My definition is not quite right. Okay. My definition is not quite right. ML said, I don't know what kind of empty list this is. So look how ML typed it. This stuff can get kind of touchy. Let's see if I can get it. So it turned out that wasn't quite a good idea. I want to return, I'm taking in an A list, and I want to return an A and another A list. So I said, okay, take the first time out of the list, return it, and return the empty list. But ML said, well, you're giving me out an item from your input list, and then you're giving me a different kind of list. It has no way of knowing that this is the empty list of A. So it says, oh, it's just somebody else's empty list. So it doesn't know that that was the empty list of A's. I could say that this is type A list. Now I'm saying that empty list of that type. No, that doesn't make sense because I don't know what A is. Oh yeah, it does make sense. Well, it probably doesn't make sense. I can make it make sense, but I got a feeling it still doesn't make sense yet. See, didn't work. Well, why? Okay, let's go back and think. I said that this is an A list. Okay, but I never said that this is an A object. So it doesn't have a way of connecting that list to that type. I said, oh, I want this to be an A list. Notice that ML turned it into a B list. It said, well, okay, X's are the A's and you're the B's over here, but it still gave me the same output. Okay, so ML's thinking was there's an input list of some type. The output, the first time in the output, has the same type as the input list. ML, to ML's point of view, the first type is always A. So X is type A. Now over here, you said the output is an empty list of this other type. You called it A. Well, ML's already used A to mean the type of X, so it relabels this one type B, but there's nothing to connect them together. So here's how I would fix this one. I could fix this example by saying that I'd have to say that X is a thingy. So X is an A thing. I don't know what A is, but X is an A thing. So that makes this a list of A things. I'm going to return X and the empty list of A things. Okay. So now I've got it fixed. This should work now. ML should agree with me now that see, A list goes to A and A list. Okay. But I had to I wanted to use the constant. I wanted to make the empty list the return value, but I had to like work at it to get the empty list to be. The empty list is highly polymorphic. So ML, when you write the empty list, ML, if you don't tell it otherwise, to ML, the empty list, it doesn't know what it is. It's the empty list of something, but it doesn't know what. So more often than not, when we write our recursive functions, when we get to the recursive functions, we use the empty list a lot. Usually, if you look carefully at those definitions, ML knows what the empty list is in those cases. Here, I'm kind of pushing things a little bit. I'm kind of pulling the empty list out of nowhere here. Yeah, the way I'm using it. I'm not See, the thing is, I'm not consing anything onto it. Okay, I'm not consing anything onto the empty list. So ML doesn't see me doing anything with that empty list. So ML says it's any kind of empty list because you didn't do anything with it. When we write our recursive functions, we'll use an empty list symbol, but we'll almost always do something like cons something onto it. But then ML will know the type of this guy. So that means that it knows what type the empty list is. As soon as you con something onto the empty list, ML knows what kind of empty list it is, as long as it knows what this thing is. Okay. Here, I did kind of a funny thing. I just pulled an empty list out of nowhere, and I didn't do anything with it. Okay. So if you kind of go back, here's the wrong ones. Okay. That was wrong. Okay. And the other one that was wrong, that was still wrong, was I tried to type the empty list, but I didn't know to type the X. So I didn't type the X, but I did try typing the empty list, and that was still wrong. Okay. And the right one was, I have to say X is an A, and the empty list is an empty list of A's. So now it's got that signature there. Okay. This signature basically forces me to do something like pull something out of the list. That's where this guy is. And then the rest of the list. Now, if I try to make the rest of the list the empty list, I have to play games. I have to force ML to realize that this is the empty list of A's by saying that X is an A and this is the empty list of A's. Okay. So, examples, I go from a simple kind of, okay, this isn't really too hard of an example. If the easiest thing to do here is just return the head and the tail. Okay, that would probably be the absolute easiest way to think about this. Just say, oh, you give me a list and you're supposed to return, you give me a list and I want you to give me back something from the list and a list of the same type. So I'll just give you back, I'll take the head. All right, or the simplest thing might be this. Here's an even simpler. Here would be even a simpler example. This might be the absolute simplest. Pull something out of the list. That's this part. And give me the whole list as the second part. If I need to come up with an A list, I have an A list. It's the input list. So here's probably the absolute simplest. Yeah. Yeah, that would, that would probably be the most straightforward, the least work. This would be the one that does the least. There's got to be something in the list, so take the head out and just return the whole list. Okay. Okay. The type puts a pretty big restriction here. The types, because of the type, we don't know anything about A, we pretty much have to return an A thing. This guy here has to come out of the list, is what it amounts to. This one has to be from somewhere in that list. Okay. Okay. Let's try one more. A pair of things of type A. That's what I get. Okay. So this thing takes in a pair, X, Y. Okay. Right now, that could be an X of type A and a Y of type B, but what I want to get back is a list of A's. Well, if I do this, I'm returning an empty list, and ML's going to say, I don't have an idea what empty list this is. So it's going to say this is a function of A's and B's to a list of C's. Like, watch. ML will now say that this is a function that takes in a A and a B and gives me out a list of C's. Okay, so see, it took in a pair of an A and a B, and it gave me out a list of C's. So that's not quite right. What if I put something in the list? Okay, well, I could put X in the list. Okay, well, let's put X in the list. Now what's ML think? An A and a B, so a pair of A and B and a list of A. That's closer to what we want. See, X got put in here. So this is a list of that type. So now the function is a pair of A and B. It's a pair of A and B with a list of A's. Now, how do I force the Y to have type A? Put it in the list with X. Stick the Y in there with the X. Okay, so this one's wrong, and this one's still wrong. Okay, but if I stick the Y in there with the X, then this becomes a list of type A, and that forces Y to have the same type as X. Now, can I vary that function a little bit? A little bit. I could do, okay, yeah. I could do the following. Here's kind of a dumb thing. Okay, notice I'm building a list of A's. But notice that, what's my list of A's? X and Y. I don't have much else to play with. I've got a thing of type A, and I've got another thing of type A. I need a list of type A. I know nothing about A. So when I cook up my list of A's, I can basically just play around with X and Y. I need to use both of them. But I do have to use both of them, because otherwise, if I don't use one of them, then it gets its own type. So I'm forced to use both of them in the new list. And I can kind of use them in any way I want. I could, they don't have to be in any kind of order. I could do a Y there. I could put an X there. I put an X there. See, I can mix up the X and Y's all I want. Okay. But notice that the type signature kind of dictates quite a bit of what I can do. I've got a pair of A's, and I need a list of A's, and there's not much else I can do. I can't use the empty list, because I could make this one right by playing the game we did a little while ago. To make it right, I have to say X is a thingy, and Y is I have to say Y is an A thingy also. And then I can say this is a list of A things. Okay. So I can get away with using the empty list, but then I have to pretty much annotate everything. Oh, I could annotate this. Let me annotate this one a different way. Let me annotate it by saying that the return type is list of A. I'm just using a slightly different syntax to do the same thing. So now I'm saying that the function takes in an X that's an A and a Y that's an A. Oh, I forgot an X of type A, Y of type A, and output a list of type A, and the output is the empty list. But that's now a list of type A. I've said it's a list of type A. So I don't end up having to use the two things I was given in, see? But I had to work a little harder to do that, to avoid using this object here and this object here. And to return the empty list, I had to work harder to make sure ML realized that that's type A and this has the same type, and that the output list has the same type that this guy had. If I drop any of these annotations, like go back over here, drop the annotation on the A, on the Y. Okay, now ML says, you give me an X of type A Y of, well, there's nothing, you're not doing with a Y, so I'm going to call it of type B, and the output list is the empty list of type A. Okay, but since I didn't do anything with Y, and I didn't tell ML anything about Y, so it gave it a polymorphic type, which was different than the X. Okay, if I drop the annotation on the X, we're back to beginning. X can be any type, Y can be any type, but the output list is a type A. But that's actually now, from ML's point of view, the third type. X has one type, Y has another type. The return value has a different type. So now ML says there's three types there. And it orders them A, B, C. So the return type is a C list. I said A list, but ML says I'm going to order these things the way I want to. A type, B type, third one, C type. It reads them from left to right. Okay. Okay. This may seem weird to you, but believe me, it's not. It's what modern programming is all about. Java is becoming a language like this. C++ is becoming a language like this. I was writing some Java code the other day, and I got an error message I'd never seen from Java before, because I was writing some weird generics code. And I realized that the error message that Java gave me was copied from ML. I realized it was something I'd never seen before, and I recognized it. It was an ML style error message in Java, but I was doing some weird generic code, and I did something wrong. I goofed something up, but the error message was an ML style error message, which means that they're cribbing from the ML compiler. They're probably literally using code that they more or less borrowed from the ML compiler, because I got an ML style error message in Java. And since we've been doing ML in this class, I recognized it. I recognized it as it didn't look anything like any Java error message I'd ever seen before. And it looked like an ML error message. Okay, this stuff it's feeding its way slowly into the whole world of programming. It came out of it was done. This stuff was all done in the 80s in ML, in the 70s and 80s. And it's taken a long time, but it might look weird to you, but when you start trying to do more advanced Java programming, you're going to run right up against the same kind of stuff. You're going to head into type inference and type parameters and weird, these type parameters are now showing up in Java just like this. And you'll see, this stuff is part of it's in C#, it's in Java, it's in C++, it's becoming part of JavaScript, it's becoming part of Python. Every prominent modern language is absorbing these ideas. So these are good things to do. Yeah, if you get comfortable with these problems, especially when I do it the weird ways. Okay, there's kind of an easy way to solve each one of these problems, and I'm kind of right here forcing you to see some wrong ways and see some oddball ways. Okay? But there is easy way. You should at least be able to come up with the easy way. And you should follow the oddball ways. If I show you an oddball way, you should be able to see why this one's wrong and why this one has to be kind of the odd way it is. Okay. And this is the one that you should come up with. If I want if the function takes in two thingies of type A and I have to create a list of type A, the only clear thing to do is put the two thingies in the list. Okay. That's the easy thing to do, and it'll give me that type. Okay. Now, this last one, I'll just point out, since this one gives you back an int, you know a lot about the int type. This one has a lot of leeway. You could do a lot with this one. This one's not going to be very constrained. It takes a list of A's and gives you back an int. I mean, you can pretty much do anything. X equals 0. Okay. Will that work? Is that good enough? I got the output int. What's the type of the input? What's ML going to tell me the input type is?
A.
Why?
The return type has nothing to do with input.
Yeah, but why didn't I get this? You're right. I'm going to get back its type A, but I want it to be a list. Now, why am I getting back type A? Why didn't, and what can I do to make it this? Why did I get only A? I got A to int, not list of A to int. There's the int. That was easy.
There isn't anything in the function to hint.
Yeah, right. So
it would be a list.
Right. I didn't do anything with X. If I didn't do anything with X, it's just type A. So what do I do with it to make it look like it must be a list? What can I put here to make ML say, oh, the input is a list?
Brackets.
Pardon me?
Square brackets.
Oh, okay. Square bracket around it. Is that what you mean, like that?
Yeah.
Okay, okay. Let's see okay, it's a list of something. It's a list of something. And well, the something was type A because we didn't do anything with it. So, okay, this should be list of A because we use the square bracket to say list of. Bingo. List of A to int. Okay. Warning, you didn't do enough pattern matching, but that's okay. Here's another one. Here's something else I could have done. Instead of putting the brackets around the X, I could have said, oh, it's X const on to X's. See, that would also say it's a list because it's made of something const on to something. Whoops, two conses. This is actually probably a little bit easier. It's a list. It's a list of something. Oh, what if I just did that? Actually, what about that? Would ML be happy with, oh, you gave me an empty list and you gave me in an empty list and you gave me out 0. What's this the empty list of? What did we say a while ago? If you give ML an empty list and you don't say anything about it, what's it an empty list of? It's a list. What's in the list? Okay. What? ML says, yeah, it's a list. The input's a list. List of what?
Is it just nil?
No, nil is, that's just another word for list. No, it's not. Nil is not what it's a list of. Nil is just another word for the empty list. So nil is a synonym for the empty list. What's it a list of? Is it a list of ints? Is it a list of strings? Is it a list of reals? What's it a list of? If I just give it an empty list and don't say anything, it's a list of
Type A.
type A. Yeah, because it's a list of A where A is it doesn't know, it's a polymorphic empty list. So it's an empty list of, of A's. So there would be the absolute simplest function. So actually, that one's kind of neat. There would be the absolute simplest function with that type. Empty list in, 0 out. Okay. And then, this is actually the X is not even really needed in there. And now this says it's a list by saying, oh, I put something in the list. So that by using the cons operator, I said, oh, the input's a list. But actually, I didn't even need to put anything in the list. They just say f of 5 takes in an empty list and gives me back 0. Okay, so that's polymorphism. Okay, all right. So let's start looking at the recursive function definitions. Okay, so let's go. Do these examples, play with these examples, talk to someone, if you got a friend in class, talk to them. These are really good problems. These are challenging. It's almost like math problems. It might actually look a little to you like doing math homework. And guess what? Yep. Yeah. The people who invented all this stuff are almost all mathematicians. This is where modern programming overlaps with modern mathematics, and it's the future of programming. So if this looks like math homework, yeah, it is. Yeah, because ML was literally invented to solve math problems. It was actually invented as a theorem prover. The history is that ML was written as an experiment in theorem proving, and it's still an ongoing experiment. It's one of the more interesting branches of theoretical computer science. Write programs that prove theorems. What was interesting is in the process of writing programs to prove theorems, they invented a modern programming language that's taking over. And that just shows that when things are driven by mathematical theory, they tend to be right. Okay, that physicists have known that for a long time, chemists have known that for a long time, biologists have known it for a long time. When ideas come out of mathematical theory, they tend to usually be pretty sound. So a programming language that came out of an attempt to prove theorems turned out to be a pioneering programming language. It took a while for it to be realized, but now ML is spreading its ideas through all of computer science. And it came out of math. It came out of a combination of mathematicians and computer scientists saying, can we write programs that'll prove theorems? So you give it the theorem and it gives you back the proof. Like, you did proofs like in geometry class in high school. Literally, that's what they'd like to do. They'd like to reproduce high school geometry. If you give this program a theorem in Euclidean geometry, it'll give you back the Euclidean geometry proof. It's one of the early forms of artificial intelligence. It was related to that work. And ML came out of that. That's why it was called meta language. It was a language for describing these abstract theorem languages. Okay, so it feels like math, and it is. The theory, the languages came pretty much out of people trying to use math to solve computer science problems. Okay, so now let's do these. There's a whole bunch of recursive function definitions in here. So let's start going through them as a dictionary of recursive function examples, because like a lot of things in life, you learn by looking at examples. Okay, the theory of recursion doesn't get you very far. It's looking at lots of examples that pretty much people learn recursion by looking at lots of examples and writing their own. Okay, now here's a little bit of explanation of the idea. The key is that what's a list? A list is either empty or it's something in front of the rest of the list. Okay, think that's a pattern. A list is empty or it's something in front of the rest of the list. Here's another way of writing it. Here's a grammar way of writing it. A list is empty or it's something in front of a list. It's recursive. See, recursive functions because you have a recursive data structure. That's a real important part of computer science. Recursive data structures are best dealt with by recursive functions. If you want to do something with that list, you say, here's what to do on the empty list. Then you say, do something on this guy, and then recursively do something on the rest of the list. That's what this thing here says in words. When you want to write a function of lists, what you do is you tell me what to do with the empty list. That's the base case for the recursion. What do you do with the empty list? Then you tell me what to do with the first thing in the list, and then add it on to the recursion on the rest of the list. And the secret is to let the recursion of the rest of the list do almost all the work. You basically tell me what to do at the beginning of the list and let the recursion do all the rest of the work. Recursion actually, instead of being harder, it actually, once you figure it out, makes things easier because it says, oh, you want to process a whole list? Tell me what to do with the first thing and then recurse on the rest of the list. You really only need to tell me what to do with the first thing. So let's see what we mean by that. How do you compute the length of a list? Okay, well, the length of an empty list is 0. Okay, that's the first step of the pattern. What to do with the empty list? The length of an empty list is 0. Okay, what if I give you a list that's not empty? So it's something in front of the rest of the list. Well, that's 1 plus. That's this part. I count the item as 1 and add it to the recursion on the rest of the list. So I count the thingy at the front of the list, which I notice I use a wildcard there because I don't even care what it is. I don't care if it's what value is in that slot. I count it and add that count to the length of the rest of the list. And that works. Okay, here's another one. Suppose I want to sum all the numbers in a list. You give me a list of numbers, I want to add them all up. Okay, well, what's the sum of the empty list? Well, there's nothing in it to add, so I'll give you back 0. What if you give me a list with something in front of it? Okay, so I'm going to take that number and add it to the sum of the rest of the list. See? I only have to worry about what to do with the first number. Add it to the sum of the rest of the numbers. That's this thing here. If I want to sum up a list, I take the first thing in the list and add it to summing the rest of the list. Okay, so I tell you what to do with the empty list, and then I say, okay, when you give me a list that's not empty, it's got something at the front of the list, I'm just going to take that guy and add it to everything left in the list, the sum of everything left in the list. Okay, so it's real simple. I don't worry about how many things are in the list. Okay, right? Now here's an example. It's not much more complicated, but we're going to step through. In this case, I want to step through what it looks like when you actually do an example in recursion. Okay, so take a list of integers and return a list of integers where you square every number in the input list. So this is going to be a little bit different. Notice that here, the output was an int. Now the output is a list. So I want to take a list in and build a list out. I want the output list to be all the numbers in the input list squared. So what do? Well, if you give me nothing, I give you back nothing. Okay. Notice this is not, now, remember we said a while ago that if you give ML an empty list, it says it's the empty list of anything, okay? But this is supposed to be an empty list of ints. The second line is going to tell ML that this is a list of empty list of ints. That line by itself doesn't tell ML a lot. This is, you give me an empty list of A's, and I give you back an empty list of B's. That's actually by itself. if I just take that line there, and I actually give it to ML by itself, ML will tell me, you gave me an empty list of A's and I gave you back an empty list of B's. See, because you didn't say anything about that empty list. You didn't say anything about that empty list. So that's the empty list of A's and that's the empty list of B's. Okay. Now, what we're doing though is we have more than one clause. See, the function square them has got, these are the clauses that was used earlier. That's a clause with an equal sign in it. And that's another clause, got an equal sign in it. So there's two clauses. This clause is going to tell ML that I'm working with ints because I'm going to take something in the list and square and multiply it with itself. The multiplication operator takes in two ints or two reals. We said this a lot of times. Takes in two ints or two reals. It defaults to two ints. So X is an int. So this is a list of ints. So this is the empty list of ints, and this is the empty list of ints. Okay. So ML went backwards to this guy after it analyzed this line. So this line by itself does not say a whole lot. The empty list in gives me the empty list out, but it doesn't say what kind of lists they are. ML by itself thinks that if it just gave it that line, it would say that this function is taking in an empty list of A's and giving me back an empty list of B's. Now, so that's the first. Now, so what do we do with the empty list? If you give me an empty list, I'll give you back an empty list. Okay. What if you give me a list that's not empty? So there's a number at the front of the list. Square the number, cons it onto square everything else. See? This will square everything else and build the list that's the square of all the things in it. So this will return the list that I want to put this number in front of. So there's the, you give me a list. If it's empty, I give you back the empty list. If it's got something in it, I square that thing and add it on to the work you do on the rest of the list. Okay, so I use this pattern. See, a list is either empty or something in front of the rest of the list. So I structure my code on that pattern. So that pattern, all my definitions are kind of structured on that. So down here, if I put, see, I'm saying I'm using clauses here. Notice that notice that when we wrote grammars, we used that thing to mean this or this, and ML uses that thing to mean this clause or this clause. This is actually kind of part of the game, is that the language of grammars is very closely related to the ML programming language. Now, the language of grammars has got, you think it's got nothing to do with ML. You use this language of grammars even if you're describing JSON or if you're describing SQL. But the language of grammars actually turns out to be very closely related to the ML programming language. All this stuff was invented at the same time by people who kept saying, gosh, we're doing the same thing over here, and we're doing the same thing over there, and there's a commonality to what we're doing. We have to try to find that commonality. They were processing grammars, and they were writing functions, and they realized that the functions they were writing looked a lot like the grammars they were writing. Okay, ML turns out to be a really good language for processing grammars because of this kind of thing. A grammar is written in clauses. We call them productions. The grammar, that was a production, and that's a production. ML is written in clauses, and it uses the same symbol to say clause 1, clause 2. Grammar says production 1, production 2. Okay. If the list is empty, a list is either empty or it's something in front of this. I write my function by saying what to do on the empty case. On the empty case, on here I return empty. What to do on the other case? See, that case there is that case there. See, list has either that case or that case. So what to do on the first case, what to do on the second case. Then this says what to do. On this case, give me an empty list back. On this case, I want you to square that number and cons it onto squaring the rest of the list. Look how it works out. Suppose I ask you to square 3452. Okay, 3452 is not the empty list. So I'm in this clause here. So I take the square of 3, cons it onto the square of the rest of the list. So that's the square of 452. All right. Okay. That's one iteration of the recursion. You can't do the cons yet. Now you can do the 3 times 3, that's 9, but you can't do the cons because you don't know what this guy is yet. So you have to process him. So process square them. That's the recursion. What does square them of 452 do? Well, it's not the empty list case, so it's this case. So it takes the first item in the list, and it takes the first item in the list, squares it, cons it onto the rest of the list, which is the 5-2. Okay, so this led to the recursion. This led to that recursion. Okay, now the fourth, I can do the 4 times 4, it's 16. I can't do this cons because I don't know what this list is yet. I can't do this cons because I don't know what this list is yet. I can't do this cons because I don't know what this list is yet. So I have to do the recursion on it. So now I'm to the recursion. On this one, I did the recursion on 5-2. So I got 5 squared recursing on square of 2. Well, what's square of 2? It's still not the empty case pattern, so it's something in front of something else. This is 2 in front of the empty list. So this is 2 squared cons onto the square them of the empty list. Now I've gotten to the end of the recursion because now I got to the base case. Square them of the empty list gives me back the empty list. Okay, now I can do that cons. 4 cons onto the empty list is, oh, I forgot a step. Oh, sorry, I have to fix that. 4 cons onto the empty list, I kind of skipped a step there. 4 cons onto the empty list is the list that contains 4. Okay, now I can do that cons. 25 cons onto the list 4 gives me 25-4. Now I can do that cons. 16 cons on the 25-4 gives me 16-25-4. 9 cons on the 16-25-4 gives me the final list. Notice how the cons were worked from the right to left. I couldn't do that cons until I finished doing that cons. I can't do that cons until I've done that square them. I can't do that cons until I've done the square them. I can't do that cons until I know what's on the right-hand side, because cons is done from right to left. Addition's done from left to right. Multiplication's done from left to right, but cons is done from right to left. Finally, I can tell you what that thing is. That thing is that list. Now that cons is doable, and it gives me 4. And that cons is doable. It gives me that 2-item list. Okay, so now I cons from right to left. So I go into the recursion and come back out of the recursion. So this shows you how a way of, now notice that when you write the function, you don't need to even really think about what's happening. The goal of recursion is for you to say, all I need to do is square the number and put it in front of the rest of the stuff. You actually don't need to think too much about what's really happening. Here I kind of show you it's good to think. It's eventually, as you do harder problems, you have to think more and more about what's going on inside the recursion. But with the simpler ones, the real goal is to say, I want to take a list and square each number in the list. So if the list is empty, I give you back an empty list. If there's something in the list, I square it and recurse on, which is going to square everything in the rest of the list. So I put this square in the front of the rest of the list squared. Okay, right? So if you think of it the right way, recursion makes things easier. You don't worry about this. It just happens. The goal of square them is to take everything in that list and square it and give you back the new list. and then you want to put this number in front of it, the square of the first number. Okay, so when you get used to this, recursion makes things easier because you don't have to worry about what to do next. It's always call the recursive function. Do the first thing, then call the recursive function. Now, later on down the page, we'll see some more complicated examples. You can make recursion a little bit harder than that, but it's still, the recursion problems become harder because you're doing harder things. And if you did them without recursion, they would probably be still harder still. So as we do harder problems, the recursion might become a little bit trickier, but that's because the problem itself is becoming trickier. But for simple things, the recursion is very simple. Okay, so there's a whole bunch at the beginning of very simple recursions. Okay, very, very simple recursions. They don't start getting tricky until, actually, almost all of these are real simple. Here's where it starts getting different. What's different here is I'm recursing on two lists. When we get to this example, it's recursion on two lists. So that becomes a little bit trickier. Okay, so all these others up here are recursion on one list, and they're almost all the same pattern. So from here up, they're all pretty simple. There's a whole bunch of fairly simple examples. It doesn't start getting a little bit tricky until this one called pair up. No, I'm sorry. The one that takes two lists. Where is it? This one. This example is different because it works on two lists. That's where things start getting a little bit different. Okay, so that's where we'll start. We'll on Wednesday or on Thursday, we'll do a few more of the simple examples. We'll do a couple more simple examples. Then we'll jump to this one where things start getting a little bit tricky when you're doing recursion on two lists simultaneously. That's a real interesting example. And then the ones after that are all kind of tricky. They're doing recursion on two things instead of one thing. Like some of them are going to do recursion on a list and a number. This example will do recursion on a number and a list simultaneously. Okay, so that's what we'll do on Thursday. We'll do a few more straightforward examples and then do some of the trickier examples. Treat this as a dictionary of recursion. And what you should do is between now and Thursday, try to read through these and see that they make sense to you. Treat this as a dictionary of recursion examples, that this is what you learn recursion from, like making sure that you understand why each one of these examples works. Okay, and then I'll give you there's going to be another homework assignment. You have a homework assignment due today, and I'll put another homework assignment up by Thursday of recursion examples. You're going to write your own recursion examples. So on Thursday, there'll be another programming assignment that'll be up where you're going to write more recursive functions. Okay. And then after that, we'll start the next chapter, these higher order functions, which really make use of recursion in kind of a non-trivial way. So we want to do a lot of good examples of recursion before we start remember, the book doesn't really say a whole lot about recursion. I think it's got like 2 pages on it because the book assumes that you've seen this before in other classes. So I think by doing all these examples here, by doing all these recursive examples, we'll do about as much recursion as you see in any class. This is a lot of recursion here. There's about 20 examples here. So these will give us a good dictionary of examples of recursion. Okay. All right. Anybody got any question before we quit? Any question? Read the recursion examples. They're really useful. Recursion, if you Google around, you'll see people telling you to avoid recursion. And the people who say that are always wrong. You can never avoid recursion. There's just way too many things in computer science that can only be done recursively. Many of the most important things in computer science can only be done recursively, like writing a compiler. A lot of the stuff in big data has to be done recursively. There are places where you can avoid the recursion, but there are plenty of the really important places, like processing a grammar. Processing a grammar writing a compiler. There's a whole bunch of very famous places where you absolutely cannot avoid recursion. So it's something that needs to be learned. It's just not something that can be avoided. Okay. All right, we'll quit there. Any last question? Any question? Okay. So read the examples of recursion, start thinking about it, and then actually what you might do is see if you could write any of these examples. Like just don't look at the example that's written, read the description of the function, see if you can write it yourself. That's a good way to learn things, is to try to do it yourself before you read the example. Like read a bunch of examples and then stop and say, okay, let me do the next one myself. Now I read 10 of them and then try to do the 11th one. Okay. All right. Well, we'll quit there and stop sharing and meet again on Thursday. Bye.